Welcome to the second lecture on paired sample test. In the previous lecture, I gave you an introduction about paired sample test. In this lecture, I am going to discuss an example for this paired sample case. Even though I mentioned it as t-test, I am going to discuss the z-test and t-test together. I told you in paired sample case, we have same sample in two occasions or in two time points. Now, we have series of values of blood sugar. The first individual whose blood sugar value is x1, second individual blood sugar value is x2, third individual blood sugar value is x3, so like that xn. And we gave a drug. Now we need to know whether there's an effect in this drug. This is a new drug, a product that we extracted from a plant. People say that this has hypoglycemic or blood sugar lowering effect. Now we are going to test whether there's a blood sugar lowering effect. Now, after giving this drug, after some time, assume that after about 2 hours, maybe 2 hours, we measure blood sugar again. This individual, second blood sugar value is y1, second individual, the blood sugar second value is y2. So like that we have n number of values of these n individuals. If there are 100 individuals, so n equals 100, so this n should be, we have 100 post-drug values and 100 pre-drug values. Now what we have to do is, we have to calculate the difference between the first value and the second value. We will create a column for the differences. So the first difference will be D1, the second difference will be D2, and the third difference will be D3. So like that, the difference of 100th individual will be D100. Now we have a separate variable as I discussed in the previous lecture. Now what we can do is, in this differences column, we can calculate the mean, which we can call as D bar. And this specific column, we can calculate the standard deviation. We name that as S. And we can calculate standard error, which is S divided by square root of n, that is standard error. Now, if we know this, we can calculate the null distribution. Okay, I will keep it somewhere here. Think that our D bar is 6. Reduction of 6 grams per deciliter in 100 individuals, and standard deviation is 2. We have 100 individuals. The first step is to calculate the standard errors. So the standard error is standard deviation divided by square root of n, which equals 2 divided by square root of 100, which equals 0.2. Now you can draw the null distribution. So the null distribution, we know that in this difference case, if there's no significant difference between pre and post values, in null distribution, the mean should be 0, because I told you even in the previous lectures, all the differences between the individuals will be plotted either side of 0. Now this mean should be 0 and standard error is 0.2. So the first standard deviation we should have 0.2 and the second standard deviation we should have 0.4. Towards minus side, so minus 0.2 here and minus 0.4. Now the next step, we have to calculate the z value or the t value. We will calculate z value first. Z equals d bar divided by standard error. So which is 6 divided by 0.2. That means 30. So this 30, this specific difference will be 30 standard deviations away in the null distribution or the sampling distribution. So we have 1 standard error, 2 standard error, 3 standard error, 4, 5, 6. So we can understand that there's statistical significant difference or significant effect in this specific drug. But the interpretation depends on whether this D bar is positive or whether D bar is negative. Why it is important here? We are interested in lower side, but our D bar is 6. How's that? Generally what we do is we have to reduce the pre-value from the post value, because we are expecting a lower value of post flung. So if the difference is minus 6, we can understand that post value is low, pre-value is high. That means this specific drug has reduced the blood sugar level. But now we have a positive value. That means even though we are expecting a significant reduction, this specific drug has increased the blood sugar level. This is one tail case. So plotting the rejection region is really important in this lecture. So let's see how to plot the rejection region here. Now we know that significant difference, but it's high. This has increased the blood sugar level. One tail case, our null hypothesis is mu A1 equals mu A2, and our alternative hypothesis in one tail case, because we are interested in blood sugar lowering effect. So this value or the post value must be significantly lower, or the pre-value must be significantly higher. So our alternative hypothesis is mu A1 is significantly higher than mu A2. And practically, ideally, mu A2 should be significantly lower than mu A1. Now, where's the null distribution? Null distribution, we know that, like discussed, in 0 we have 0.2, 0.4, minus 0.2, minus 0.4. But actually, once we standardize this one, in standard normal distribution, we know that mean is 0, standard deviation is 1, 2, minus 1, minus 2. Actually, those values are minus 2. I told you about the standard deviation and standard normal distribution in one of the previous lectures. Now, this value is 30 standard deviations away. Actually, this standard deviation is standard error because this is sampling distribution. Sampling distribution, so standard deviation is the standard error. Standard error is the standard deviation of sampling distribution. Now this is somewhere 30 standard deviations away. Now we know that significantly higher value, but our null hypothesis states that this should be significantly lower. If our rejection region is 5%, rejection region is 5%, if it is two-tailed, in Z distribution, the cutoff values are in both sides, in 1.96 here and 1.96 in the minus side. But now it is one tail case. The second value should be significantly lower, and we have to plot 5% in lower side. So it should be something like this. You can go and find out the probability of this red color part in your Z table, and you will get this value as minus 1.64. Now in this specific hypothesis testing, as this is one tail case, ideally the calculated value, Z calculated value should be higher than Z table value. This is critical point. Higher means either it can be high towards positive or it can be high towards negative. So actually this value should be less. But if you forget this minus, this should be higher value. Now we know that of course it's 30 is higher than 1.64 minus, but in order to reject this should be minus value or minus 1.64, and this value should be something high minus value, but it is totally opposite. So actually 30 is higher than minus 1.64, but in order to reject, as our alternative hypothesis is other way around, we can't reject the null hypothesis. So this null hypothesis H naught mu A1 equals mu A2. Even though this null hypothesis is this, we are interested in our hypothesis mu A1 or the pre1 should be significantly higher than mu A2. But what has happened is something other way around. So we can't reject the null hypothesis. And you need to understand that in one tail case, we are interested in 5% region in one side. So what to do in t-test? T-test, using the same formula, you have to calculate the t-value, and the t-value will be same as the z-value, but you have to find out the significant value in t-tail. Even you will get the same result as our value is 30. It's very high value. But the high value is in positive side. So what we need is a significant value in lower side, because this is one-tail test. I hope you are clear about paired sample t-test. Next lectures we will discuss about hypothesis testing for proportions. Thank you very much.